Okay, so so today we're going to go on to equations, and we're just going to introduce some terminology. I think most of you have probably seen this stuff before. So right, so up until now we've had these sort of mathematical expressions. Right, we've had mathematical expressions, things like 3x plus 7, 1 over, let's say, like x squared plus 1, 1 over x, 1 over x plus 2, things like this. So we've had these sort of mathematical expressions. At this point, we introduced some terminology. One is domain. So if we're thinking about an expression, what we mean by the domain is all values of the variable that are reasonable. Okay. So for example, in this case, 1 over x, your domain, x cannot be equal to 0, right? X can't be 0. Your domain is the whole real line, but the whole real line excluding 0. Okay, right? You could write that as the domain is x can be a real number, but x cannot be 0. Right? Right. In this case, your domain is x cannot be -2, and so on and so forth. Okay. Another notation for this is the real line excluding 0. Okay, so this mark means excluding, just to introduce some notation. Okay. Okay, so domain, right? So domain. Another term is constants. So constants are numbers that remain fixed, right? Numbers that remain fixed, right? So here, 3 and 7 are your constants. Right here, you got a 1 and a 1. You got some. These things are constants, right? Yes. Sometimes you'll have something like this. Cx, like ax plus b, right? And we think of the x we usually consider to be the variable. So variable, right, are right, any quantities where the value is not fixed, quantities where the value isn't fixed, right? But so usually one uses letters at the beginning of the alphabet for constants and letters at the end of the alphabet for variables. Okay, so numbers that remain fixed, even if unknown. So sometimes you'll see something like mx plus b, right? M is some fixed constant. You don't know exactly what it is. You don't know what it is. It's just specified by m, but you don't consider it to be a variable. Okay. And so these guys are usually represented by things like letters like A, B, C, letters at the beginning, and these are represented by letters at the end of the alphabet. And this is an old convention from the creation of algebra centuries ago. Like I think in the first algebra book they used this convention, and it's sort of stuck since then for hundreds of years. Okay. Okay. So okay. And then, constants, variables, and then an equation is when you demand. So when we demand that one expression equal another, that one expression equal another. Right, like. If I say 3x plus 7 equals 0, right? That's an equation, right? Because you're saying I want this 3x plus 7 to equal to 0, right? I want x squared plus 1 to be 3x plus 7, whatever. So things like this, right? So I'm sure you know all these things, right? So like ax plus b equals 0, ax squared plus bx plus c equals 0, right? These are all equations. Okay, and right. So these types of equations are called linear equations. Linear equations. These types of equations are called quadratic equations. Etc. Etc. Okay. And then the last term I want to introduce is the solution set. So solution set, you have some solution set of an equation is the set of values for the variables that make the solution make the equation true. Okay, so so for example, here you've got this equation, 3x plus 7 is equal to 0. What x makes this true? What x makes this true? Makes this 3x plus 7 equal to 0. X would have to be, can anyone just do it in your head?
Negative 3.5.
Negative 3.5? I don't, who?
Wait. Never mind. Sorry.
This is a 3.
I thought it was a 2.
This is a 3.
Yeah.
Okay. Negative 3.5 is correct. Okay, so yeah, so that would be the solution, right? That would be the solution set, right? If this is my equation, then x equals 3.5 is the solution, right? Right. So it's the set of values for the variables that make the equation true, right? So like 1 doesn't work, basically, I mean, in this case, nothing except for 3.5 is a solution for this. Okay, so right, so the game we want to play for the game we want to play for in this chapter is basically how do you find solution sets? How does one find solution sets? Okay, so that's basically the main point of this chapter, this section. Okay, so right, so for example, somebody gives you an equation, it looks like this, x over 3 plus 2x over 5 equals negative 11 over 5. Okay. And says, what x makes that true, right? What x makes this into a true statement? What x solve this? Okay. And so the way you want to think about it is that what we're going to do is we'll simplify the equation using legal moves. Okay. So there are a few things that you can do that are legal. First off, the 0th one is to just use properties of numbers. So like, you know, you can combining fractions or adding things together or this sort of thing. So just use basic properties of numbers. That's of course fine, right? I can take these two things and I can add them together, right? That's, you know, that doesn't change anything. Okay. Another thing that you can do is you can add or subtract the same quantity to both sides. Right? If I have this equation like this, it's okay for me to add, you know, some number to both sides as long as I add the same number. Right? That doesn't change the solution set. Right? Okay. Another thing you can do is you can multiply both sides by the same quantity. Actually, I've just lied to you. That's not true, actually. What's wrong with this statement? Is it okay? Suppose I have an equation like 3x equals 7, and I say, okay, I'm allowed to multiply both sides as long as I multiply both sides by the same constant. Then the solution set doesn't change. Is that really true? Olivia, why not?
No, it's not true. Because depending on what number you're multiplying it by, it can become like significantly greater than the other number.
Well, it's actually almost true. This statement is actually almost true. Like, does anyone know what I'm trying to get at here? This is actually true in general, except you have to be a little careful. It has to be non-zero. It has to be non-zero. So like, if I multiply both sides by 5, say, 15x equals 35, right? The solution set actually hasn't changed, right? The appearance of the equation has changed, but the solution set hasn't changed, right? If I multiply both sides by, say, 1/3, right? And I get, x equals 7/3, right? Then the solution set is still the same. Okay, it's actually okay to multiply an equation by a number as long as it's a non-zero number. Does that seem okay? Good. that's familiar, right? And these are basically it. These are basically all you want to use to solve your equation. Okay, so here you say, okay, so what would happen if we multiplied by 0? I've got this equation, 3x equals 7, and I say, okay, I'm going to multiply this by 0. I get 0 equals 0. Okay, what's the solution set of 0 equals 0? Is it okay if x is 1? Will 0 be equal to 0? Yes, right? If x is 1,000,000, is 0 going to be equal to 0? Yes. So by multiplying by this, I sort of lose all information, and the solution set becomes the entire line. Okay, so this is why you can't multiply by 0 on both. If you multiply by 0 on both sides, you've changed the solution set drastically. Okay, but if you do only these things, then you don't change the solution set. Okay, so that's why I said that these are the legal moves, right? For another sort of crazy example, right? If I suppose I subtract 7 from this side, but I subtract 6 from this side. Have I changed the solution set? Yes, very much so, right? Right. So you have to subtract the same thing from both sides, right? You have to add the same thing. I've added, -7 to this side and -6 to that side, right? So, there are all sorts of things you can do, but you're only allowed to do the ones that don't change the solution set. Okay, so that's these are the ones we're going to stick with for the moment. Okay, so you say, okay, suppose we want to do this. Well, we want to. So the question is, figure out what x makes this work. So figure out the solution set. How would you do it? Well, you would take this thing, you say, okay, I'm going to use just basic properties of numbers, right? I'm going to combine these things together. So I'll make I'll make this guy 5x over 15, right? I'll make this guy 6x over 15, right? And maybe on the right-hand side, I'll also, yeah, this is, again, what I've been calling multiplying by 1, right? So I'm multiplying this guy by 5 over 5, right? I'm multiplying this guy by 3 over 3. I'm multiplying this guy by 3 over 3 also. Okay, right? And I'm doing that in order to get a common denominator, right? So that it'll be easy to work with. So, so what I'm doing is using the basic properties of numbers. It's okay. So let me just say that here's the property. Here's what I'm using. The zeroth move. Right. So just using basic properties of numbers, it's okay to multiply by 1. It's always okay to multiply by 1. Right? You're not changing anything. So you got 5x over 15 plus 6x over 15 equals minus 33 over 15. Right? Okay. And then here, say I multiply both sides by 15. So I'm going to use property number 2. It's a legal move to multiply both sides by the same number. So I multiply both sides by 15. 15 times this, and then I multiply this thing by 15. Right? You see what happens. You get some cancellation. Right? 5x plus 6x equals negative 33. I combine these together using basic properties of numbers, right? So 5x plus 6x is 11x equals negative 33, right? So that's here, basic properties of numbers, right? And then I'm going to multiply both sides by 1/11. Right? So then multiply both sides by 1/11, because that's okay by property number 2. Right? So I get negative 1/11 of negative 33. And that gives me this equation, x equals negative 3. Okay. I think I said before that this arrow means then. Right? So you say this then or implies. Okay. So you get this thing, you multiply by both sides by 1/11. You get this thing, you multiply, and then you get this thing. Okay. So what's the point here? That this equation and that equation have the same solution set. Right? This equation and that equation have the same solution set, so you know that the solution set of this is negative 3. Right, and maybe I should put arrows all along to show you that we start from here, then we multiply, then we multiply everything by 1, then we multiply both sides by 15, then we, et cetera, right? So this implies this, implies this, implies this. So this is how math works. Okay, let me remark that you could go backwards, right? From here, I could, I could multiply. No, I mean this is the same thing, right? So this is actually the same thing as this, right? Right. And then from here, I would multiply both sides by 11, and I would get this. And all of these arrows are reversible. Right, I can go from here back up to here because this is I've just multiplied everything by 1 from here to here. Okay, and why these are legal? Why these why these moves don't change the solution set is because they're reversible. Okay, so this is sort of a more higher level comment, but remark that the moves don't change the solution set because they are sort of, in some sense, reversible. Okay. And that's why multiplying by 0 is not a good move to do, because it's not reversible, right? If I start from an equation, x equals 3, and then I multiply everything by 0, and I get to this one, how do I come back to the original? You can't, right? Are you going to divide by 0 somehow and get back to here? It doesn't work, right? So that's sort of the distinction between what's legal and what's illegal. Okay. Let me put up a sort of try this. Okay, so here's one. 1 over x plus 5. So this is more complicated. Minus 1 over x plus 5 equals 2 over x minus 3 plus 2x plus 2 over x plus 5 x minus 3. Okay. The first thing I want you to think about is what's the domain? What's the domain? And then I want you to think about what's the solution set. Okay, like what would you do to try to get to the solution set? And I don't want you to actually go all the way through it, but I want you to just make some initial moves. Like, what would you do if you were given this and you wanted to simplify it into a form that, is easy to read the solution set off of, right? The goal is basically to get this ugly thing into a form where the solution set is obvious, right? Here, x equals minus 3. What x solves this? Minus 3 solves this, right? Here it's not so obvious, right? But you know that these two equations have the same solution sets. So try to change this into something where the solution set is obvious. Okay, turn to somebody nearby and talk with them.
That's so far.
Okay. First off, what is the domain for this equation?
What?
Stella?
So I think I put that x cannot be negative 5 because the 1 over x plus 5, and then x cannot be 3 because of the 2 over x
That's right. That's right. So anything is okay, but not. You know that x can't be 3, can't be negative 5, and it can't be 3. So fine. Great. Okay. Okay. So now, keeping that in mind, what would we do to solve this? How would we solve this sort of thing? Anybody want to say what we could do? Yes, Olivia?
You can multiply the first part by x minus 3 over x minus 3.
Okay.
Which is 1.
Okay, so we put in this 1 here, right?
And then, should I keep on going?
Yeah.
And then you can multiply the other part, the 2
Mhm.
over x minus 3 times x plus 5.
Right. So you multiply, again, we're trying to get common denominators, so we play this game, right? We get this sort of thing. Right? And then we can use, say, like, what would you do after that? Say?
It's supposed to be x plus.
Oh, did I mess up? This should be minus sign.
And
This
x
should be
plus
plus 5, thank you.
So then it would be x minus 3 over x minus 3 times x plus 5 equals 2x plus 10, or I simplified it, but over x plus 5 times x minus 3, and then plus the 2x plus 2 over
Mhm.
x plus 5 times x minus 3.
Okay.
And then you can multiply all of that by x minus 3 times x plus 5, which just simplifies it to x minus 3 equals
2x plus 10.
plus 10.
That's 2x.
Yeah. And then you just subtract or add 3 to the other side.
So we're going to add 3 to both sides. Right, so we get the minus 3 plus 3, that becomes 0.
And then you can subtract 4x plus from both sides.
Okay, so we're going to, sorry, we're going to add 3 minus 4x to both sides.
So then you get negative 3x equals 15.
Negative 3x equals 15.
And then the solution is x equals negative 5.
X equals negative
That cannot be true.
What?
That cannot be true.
Which doesn't
because
work.
The domain
Yes.
is x cannot equal negative 5.
Yeah, so x cannot be negative 5 or 3. Yeah. Okay, so this is kind of a funny problem, but let's, ignoring that last problem, this is how you would do it, right? Everybody okay with that? Everybody okay with that? Right, so you have this equation, right? You use basic properties of numbers to get a common denominator, right? Right, so here we've gotten the common denominator, and then we use this business of multiplying both sides by the same number, right? Right, so we multiply both sides by x minus 3 times x plus 5 on both sides, right? And then we get this thing, and then we just use basic properties of numbers again, and then we get to here, we divide both sides by negative 3, and we get this. Okay, right? So what was the trouble what was the trouble? This is okay as long, all of these moves are legal as long as x is not -5 or 3. Okay. The thing is that, right, for this to make any sense, x can't be 3, right? For this to make any sense, x can't be -5. So we've actually, when we do this sort of thing, we're assuming, we're keeping that in mind, that x can't be -5. So like, secretly, we're saying this is true as long as x is not equal to -5 or 3, right? And similarly, when we got to here, we multiplied both sides by this thing, right? That's okay as long as this is not 0, right? But if x were -5 or 3, we would be multiplying both sides by 0. Okay, so that would have been illegal, right? So we always have to keep in mind, we're saying in our domain. So as long as x is not -5 or 3, right? And so we get to the bottom and we say that this is what the solution would be as long as x is not equal to -5 or 3. And that, if you keep that stipulation in, that gets rid of this, right? Then that says, okay, there is no solution. Okay, the only thing that works is x equals -5, but we're constrained to within our domain of x can't be -5 or 3. Okay. Okay, so you have to be a little bit cautious when you're multiplying by things involving the variable, because you could be multiplying by 0, right? If x were -5, then what we did here was multiplying both sides by 0. Okay. Okay, and that's problematic. Okay. So the way that the book, you can sort of prevent this from happening in 2 ways. One is you're just making sure that you know what you're doing along the way, right? So just like keep in mind, okay, this only makes sense within this domain. This only is a legal move within this domain, right? So you can, one way to avoid these false solutions is to just keep your sanity. Okay. And then the other way is the book says, the book gives the following advice. It says, multiplying by expressions involving the variable may introduce extraneous solutions. So recheck solutions in this case. That is, they suggest that at the end, you take your solution and see if it actually works. Okay, and if you check that, you'd say, okay, is this a true solution? You plug it in, you say, oh, actually, I can't even make sense of this from the very beginning. So that's another way to do it, but I think it's sort of smarter to say, to know what you're doing. But this is also fine. You'd say like, okay, I'm just gonna solve it. I'm gonna be reckless. I'm gonna solve it, and then recheck my solutions at the end. Okay, so that's another way to do it. Any questions about that? Okay. Okay, let me, okay, so a couple other things are introduced in this chapter. One is something called something that you probably kind of knew all along, but never had it formally stated. It's this thing called the zero product property. Zero product property of numbers. So it's this property of numbers. Does anybody remember from the text what the zero product property is? You read it? Anybody remember? Can anybody tell me what the zero product property is? it is, let me just say it. So it's the following that, so if P and Q are numbers, then PQ equals 0 if and only if P or Q is 0. PQ equals 0 if and only if P or Q is 0. So this, like, if this happens, then that happens. If that happens, then this happens. Okay, this is what we call, this double arrow is called if and only if. Okay, what it means is that the two statements are logically equivalent. The two statements are logically equivalent. Okay, like if this happens, that happens. If that happens, this happens. Right? They're basically the same statement. These are basically the same statement. Okay. So this is something that you kind of know instinctively, right? If P or Q, if one or both of P or Q is equal to 0, then certainly the product is going to be 0, right? Right. If one of these numbers is 0, the product is going to be 0, right? Right. But even stronger, if the product is 0, then one of them has to be 0, right? The only way you can get 0 is if one of these guys is 0, right? Does it seem reasonable? Yes. Right. So this is something that you probably knew all along, but never stated. Those of you who are familiar with matrices, anybody seen matrices before? Some of you see matrices. There are different systems in which this is not true. For matrices, you can have two matrices that are both non-zero, and you multiply them and you get the 0 matrix. Okay, so there are worlds in which this is not true, but for numbers, it is true. Or if you've seen things like Z mod something. Anybody heard this term, Z mod? It's like a clock. So Z mod 12 is sort of like the clock world, where all numbers are between 1 between 0 and 11. Okay, so like 3 times 4 is 0 in the clock world, right? Because 3 times 4 gets you back to the 0, right? And here's your clock. I guess this is not a real clock, but a mathematician's clock. Right. Starts from 0. Right. So 3 times 4 is 0. Right. So in this sort of the clock arithmetic world, the 0 product property isn't true. That's maybe simpler than matrices. Anyway. Okay. So 0 product property. And the way we use it is as follows. So its use is as follows. So for example, we use it in finding solution sets. As follows. So if I have something like x minus 3, 2x minus 2 equals 0, right? Suppose I simplify my equation and I get something like this. Okay. Well, the 0 product property says, well, that that's the same thing as saying that x minus 3 equals 0 or 2x minus 2 equals 0. 2x plus 2 equals 0. Right? And so what I get is that x equals 3 or x equals -1. Right? So it allows you to go from something like this to saying, all I have to do is look at the individual factors. Right? I don't have to solve this whole thing together. I can say, well, by the 0 product property, this means that this has got to be 0 or this has got to be 0. Right? So I can do them independently. Okay. You've seen this sort of thing before, but maybe didn't realize that it had to do with the 0 product property. Right? So, right, if I had something more complicated, right, x minus 3 2x plus 2, x minus 7 equals 0, right? It's got 3 factors. That's still okay, right? I'm just going to use the zero product property. Zero product property, you know, this is, it's written in terms of 2 numbers, but it could be for more than 2 numbers, right? So the zero product property says this is the same thing as saying that x minus 3 equals 0, 2x plus 2 equals 0, x minus 7 equals 0. And so my solution set is going to be 3, 3, negative 1, 7. Right. Okay. So this is useful. Right. I think you probably seen this thing before, like when you're factoring quadratic equations and stuff like that, right? You have some quadratic expression like 10x squared minus 13x plus 3 equals 0, right? And then you, by some way, you factor it, you get 10x minus 3, x minus 1 equals 0. And you do some factorization, and you say, okay, so that means that x has got to be 3/10 or 1. Right? Yes, right? You've done this before. Yes, right. You've done this before. I think maybe the only thing that's interesting here is that why is it okay to just do this in pieces? It's okay to just evaluate these equations individually, right? We evaluate these equations individually because of the zero product. Okay. So, okay. Right. Here's a more complicated example. What's called a quartic equation. So x to the 4th minus 2x cubed plus 3x minus 6 equals 0. I think this was on the diagnostic test, right? I think I asked you to factor this thing on the left. Anybody want to factor that for me? What right now? What's your name?
Meredith.
Meredith. Do you want to do it, Meredith?
I don't think I ever learned how to do that.
This one is just a trick.
Okay.
Yeah, and you should not have learned how to solve 4th degree polynomials. Yeah, that's actually really crazily hard. Yeah, so there's actually a story. There's actually kind of a story involved with this. So, like, solving quadratics, there's a formula, right? You all learn the quadratic formula. Actually, for cubics, there's a formula also. There's a cubic formula that was known to this guy named Cardano, an Italian mathematician in whatever century, in the Middle Ages sometime. But within his school of mathematics, they kept it as a secret. So so that they could solve cubic equations, but nobody else. Later, people figured out a way to solve quartic equations. They found a formula for quartic equations, and then the question was: is it possible to solve quintic equations? What about fifth order polynomials? Is there a general formula that works for them? And people tried very hard to find a formula. But it's only until I think the 18th century that this guy, Galois, managed to figure out that there actually is no formula. There is no general formula. He showed that it's impossible to find a general formula for quintic and above polynomials. And so, don't try to do it because it's been mathematically proven to be impossible. Okay, so that's one good thing about mathematics. Sometimes you can say, there's no way to do this. Galois actually died when he was, I think, 21 years old, 21 or 23, 21, I believe. And the story is, I don't know how, actually people say this story is not true, but I'm going to tell it to you anyway. The story is that he was involved with politics, and so for whatever reason, he was challenged to a duel and his opponent was an expert marksman. So they were going to fight with pistols, I guess, with pistols. And his opponent was an expert marksman, and he expected that he would die. So the story is that he spent the whole night writing this letter. They actually have this letter to his friend, explaining all of his theories of mathematics, like how his ideas work out, how it shows that these things can't have solutions, and so on and so forth. And desperately wrote down all his ideas, and then went and was killed at age 21. So that's the romanticized story. You can look up the real story, but that's the story that I read, that I learned. Okay. Sorry, let me just do this quickly. So there is a formula to solve quartic equations, but we're not going to use it. It's complicated. Instead, there's a trick to this one. You do some factoring. You say, okay, I pull out x cubed out of this one. And I see I've got an x and a minus 2. I pull out a 3 out of this one. I see that I have an x. I see about x minus 2. Okay. Right. So just by luck or whatever, you notice that there's a common factor. There's an x minus 2 here, there's an x minus 2 here, right? And then you distribute, right? You use the distributive property backwards. And you say, okay, so this is x cubed of x minus 2 and 3 of x minus 2. Right, so altogether, I've got x cubed plus 3 times x minus 2. Right, so use the distributive property, right? If I were multiplying this by this, I could distribute the x cubed times this, and then the 3 times this. I'm just using the distributive property in the reverse direction. Okay, so you get this, and you say, okay, what does that tell me? By the zero product property, I can solve these separately. Right, x minus 2 equals 0, x cubed minus plus 3 is equal to 0, and you see that x has to be a cube root of negative 3. Right? X has to be a cube root of negative 3, or x has to be 2. Okay. So it looks like in our world that there are two solutions. Okay. And so this is how you use the zero product property, to solve these sorts of things. Right? If you can factor this into a bunch of product into a product of expressions, you can set each of those expressions equal to 0 and then solve them independently. Okay. Let me just throw in one last thing, that in fact, whenever you have a degree 4 polynomial, there are actually four solutions. So here are 2 real solutions. If you do a little bit more math, you'll find out that this thing actually has 2 complex solutions. So it has 2 complex solutions. There are complex roots of cubic roots of negative 3. So they're just hiding. So don't worry. There actually are 4 solutions. Okay, that's it for today. Sorry to keep you over. So we finished 1.3. So the homework will include the stuff on the syllabus under 1.3. Okay, and I'll send out a note about that later.